All right. Now let me tell you the story about the Bella-Lovas's two families theorem. So in 1965, Bella-Lovas was an undergraduate student at the university in Hungary, and he was interested in some other problem. He was not like, nobody asked him to prove the two families theorem. He had some other problem proposed by Erdős-Heiner and Moon, and that to prove that he invented this two families theorem, which was a lemma in his paper. So I'm going to show you the this more original problem, which made him to invent two families theorem. So let me tell you what Helly's theorem. This course is not about Helly's theorem. Helly's theorem, if you want to learn more about Helly's theorem, you can take the discrete geometry course at KAIST. Right. So Helly's theorem is about convex sets. So, like, if you have a family of convex sets in Rn, let's say F is family of convex sets in Rn, and N has the property that every set of at most m plus 1 members have, if every set of m plus 1 members have a common intersection, then all members have a common intersection. So for instance, in R2, let's think of R1, right? So convex sets in R1 is just interval, right? So what is a convex set? If you have 2 points and any convex linear combination also lies inside set, that's convex set. So the convex sets are the intervals. And if you have a set of intervals where every 2 of them intersect, so every 2, so this picture it's not true. So these 2 intersect, but these 2 never intersect. But if you have a set of intervals on the real line where any 2 of them intersect, then there will be a common point where all of them intersect. In this picture, there is a common point here, right? All of them intersect. So that's in R2, in R3, in R1. In R2, if you have a convex set where any 2 intersect, then there's a point, not this one, there's a point here which belongs to all of them. So that's Helly's theorem. I'm not going to discuss the proof of that. Now, people wonder about the simplification of Helly's theorem, in particular for finite cases. So let me tell you the easy statement, right? So about finite sets, right? So let's say F be an R uniform family of sets, okay? If every set of R plus 1 members intersect or has a common element, then all of them all members have a common element. Right, so instead of dimension, I'm talking about the size of the set, right? So I'm talking about uniform families. So what is the proof? So suppose that. So choose a count example with a minimum cardinality. So let F be the A1, A2, AM. Now, trivially, M has to be at least R plus 2. Why? Because if M is at most R plus 1, then by the condition given by the lemma, so this condition already says that all of them have a common intersection. So we know that AI, so this is empty. This is given, right? All right. Now what do we do? Since F minus AI is not a count example, there is element A, let's say, I don't want to call it AI, because let's say element BI in the intersection of all others, right? Okay, so if B1, B2, Bm are all distinct, then what can you say? Then AI contains, okay, let's say A1 contains B2, B3, Bm, right? But that means size of A1 is too big, right? So we know that, but A1 is only R. So the contradiction. Right? Remember, M is bigger than R plus 2. So some of them are equal. So there are I different from J such that BI is equal to BJ. Then all AI contain all members contain BI by definitions, right? Because BI is contained in all of them except possibly AI, but AI also contain BJ, but BJ and BI are same. So that's easy. Right. Now, in 1964, Helly, China, and Moon were thinking about the variation. So let me state the theorem. They talked about the similar problem on graphs, right? So let F be a family of edges Oh, no, okay, so not this way. So let G be a graph. If any set of at most S plus 2 choose 2 edges can be covered by S vertices, then all edges can be covered by S vertices. So when I say cover, right, so if I have a graph like this, and to cover all the edges, I just need to have a set of vertices, so that every edge is instant with at least one vertex inside of that set, right? So let me say again, a set S of vertices covers a set X of edges if every edge in X is incident with some vertex in S. All right. Okay. And this bound is best possible. Why? Think of the complete graph on S plus 2 vertices. Right? Now, when I take S plus 2, choose right? If we this graph, the number of edges is S plus 2, choose 2. And yeah. Why is this? Right? That's number of edges. Right, so if you take any set of S plus 2, choose 2 edges in this graph. Oh yeah, so that means set of all edges, right? And you can cover them by, you cannot cover by S vertices because there's one edge remaining, right? If you take S vertices, there's one edge remaining. Right. So how do I say this is best? Like, in what sense this is best possible? Oh yeah, so instead, so if you have a bound which is better than S plus 2 choose S, then I give this graph. And if you don't select all the edges, then you can pick S vertices so that the complement is not an edge, right? That covers every edge in the set. So this satisfies the property that any set of less than S plus 2 choose 2 edges can be covered by S vertices, and yet not all edges can be covered by S vertices. So this shows that the bound S plus 2 choose 2 is tight. Now, once you have a theorem on a graph, people may wonder what happens if it's in a hypergraph, right? So it's natural to ask questions about the hypergraphs. Instead of graph, so graph can be seen as a 2 uniform hypergraph. So every edge has size 2. What happens if it's a hypergraph, R uniform hypergraph? So that's what Bulovas proved. This was initially proposed by Erdős-Heine and Moon, I think. So Bulovas, in 1965, when he was undergraduate student, he proved that if, okay, so let H be an R uniform hypergraph if any set of and most R choose S choose R edges can be covered by S vertices, then all edges can be covered by S vertices. All right, so how do we prove it? So assume that, suppose not, yeah. Suppose not take H as the minimum count example. All right, and then the number, no set of S vertices can cover all edges of H, right? Because that's the assumption, and that A1, A2, AM be the edges of H. For each AI, there is a set BI of vertices, BI of S vertices, covering H minus AI, right? Because H is a minimum count example, so when I delete one edge, then it's no longer a count example. Therefore, there's a set of vertices covering all edges, right? So in other words, this BI belongs to like intersection of AJ, where J is different from I. Right? Now, AI intersection BI, what is that? This has to be empty, because otherwise H is no longer a count example. Right? Because if there's a vertex that belongs to both AI and BI, then that vertex is instant with all the other edges and also instant with AI. Right? And AI intersection BJ, let's look at that. This is non-empty because that's the definition, right? Because in BJ, each vertex appears in all of AIs except AJ. Now apply the two-family theorem. Then we prove that M is the most I plus S choose R, right? So that means whenever you have an example where not all edges can be covered by S vertices, then there exists the subset of edges of size and most R plus choose R with the same property that not all vertices, not all edges can be covered by property. But this is contradiction. Right? What's the contradiction? Yeah. Right. Then by the assumption A1, A2, AM can be covered by S vertices, contradiction. All right, so that's the proof. And when R is equal to 2, this is exactly the Erdős-Heiner-Moon theorem, right? Because two uniform hypergraphs are the graphs. Okay. All right, so that's the application of Bulbas's theorem.